We say time more than almost any word in our language. What time is it? I don't have time. Time's up. But strip it down. Operationally, time is just a label, a tag, distinguishing one moment from another. That's it. And yet that simple label breaks physics, bends reality, and may not even exist. So what are you actually counting every second of your life? What if I told you that every moment of your life, every breath you have ever taken, every word you have ever spoken, every thought that has flickered through the 3 pounds of electrochemical jelly inside your skull, still exists? Not as a memory, not as a record, but as a place, as real and fixed as the city of Alexandria or the Himalayas, sitting there in a landscape we simply cannot see because our senses are not built to look in that direction. To understand this, we have to imagine something difficult. We have to take the familiar 3 dimensions of space, the left and right, the up and down, the forward and backward, that we navigate every waking moment, and we have to add to them a 4th, not metaphorically, not as a literary device, but as a genuine geometric direction. That 4th dimension is time. Together, the 3 of space and the 1 of time weave into a single fabric, a unified structure that physicists call space-time. And once you accept that time is a dimension rather unlike the other 3, a dimension through which we move, as the mathematician Hermann Minkowski understood, with a velocity we cannot help but carry, the consequences are strange beyond any intuition nature has equipped us to handle. Imagine the entire history of the universe, not as a story unfolding, but as a sculpture already complete. Every event that has ever happened or ever will happen occupies a fixed position within this 4-dimensional block. The birth of a star in the Eagle Nebula, the fall of Rome, your first kiss, the heat death of the last sun to burn in the distant future. All of them are in there, each at its own coordinate, none more real than any other. This is the block universe, and it is not some fringe speculation, but a direct and nearly inescapable consequence of Einstein's relativity. In this view, the past has not vanished, and the future has not yet to arrive. They are all simply there, the way New York exists even when you are standing in Delhi, the way the far side of the moon exists even when you can only see the near. The whole of reality, past and present and future, is etched into the block like veins in marble. Now picture a human life within this architecture, not the life as you experience it, moment bleeding into moment, but the life as it would appear to a being who could perceive all 4 dimensions at once. What would it look like? It would look like a long, wavering thread, a world line, the physicists call it, beginning at the instant of birth, coiling and looping through decades of motion and rest, of walking and sleeping and loving and grieving, and terminating, at last, at the coordinates of death. A newborn enters the world in a hospital bed, and decades later, departs it from another, and between those 2 points, the world line traces an unbroken path through the block, a slender filament of carbon and water and electricity that once, for a brief interval, knew it existed. Every person who has ever lived has left such a thread in the space-time fabric. They are all still there. Every thread of every ancestor, every world line of every creature that crawled through the Cambrian mud, frozen, permanent, woven into the structure of a universe that does not forget. And here is the vertigo that comes when you hold this picture in your mind. If the block universe is real, then the you of 10 years ago is not gone. The you of 10 years from now is not merely possible. They are each as existent, as fixed, as present in the space-time geometry as the room you sit in now. The sense that time flows, that the present is a moving spotlight advancing along the fourth dimension, illuminating one slice of reality before abandoning it to darkness. That sense, however overwhelming, may be nothing more than the particular way a conscious organism processes its passage through the block. The spotlight moves, the sculpture does not. But if past and future are equally real, equally frozen in the geometry of space-time, then something deeply unsettling follows. The freedom to choose, the open texture of the unwritten tomorrow, the conviction that what happens next is not yet decided. All of it would be an illusion, a trick played on us by brains too limited to see the whole shape at once. And that raises a question we are not yet equipped to answer. A question that will pursue us through every chapter that follows. If the future already exists, laid out and fixed in the block, then what exactly is it that you are moving toward? And do you have any choice in the matter at all? There are two ways to contemplate a river. You can stand on its bank and watch the water flow past, moment by moment, each ripple arriving from upstream and vanishing downstream. And in this experience, the river exists only in the present instant. What has passed is gone. What has not yet arrived is not yet real. Or you can climb to a height, far enough above the valley to see the entire watercourse at once, from its source in the mountains to its delta at the sea. And in this vision, nothing flows at all. The river simply is, complete and still, a single object stretched across the landscape. These are not two rivers, but two descriptions of the same river, and the question that now confronts us is which of these descriptions applies to time itself. The first view, the one that matches our everyday experience with such fidelity that most of us never think to question it, holds that only the present is real. The past existed once, but exists no longer. The future will exist, but does not yet. Each moment gives way to the next in a ceaseless procession, and reality is confined to the razor-thin edge between what was and what will be, the luminous, ever-advancing frontier we call now. This is the common sense view, the view that every human culture in every age has, without exception, simply assumed to be true. Augustine felt it deeply. He confessed, in his Confessions, that he could not define time. He knew what it was until someone asked him to explain it, and then he did not know. But Einstein asked, and the answer that fell out of his equations, with the quiet inexorability of arithmetic, was that the river does not flow. In the block universe that relativity reveals, every moment that has ever existed or will ever exist is equally real, coexisting in a four-dimensional structure, as fixed and complete as a sculpture. Your birth, this instant, and the last conscious thought you will ever have are not successive states of a world in motion, but simultaneous features of a world at rest. The past has not vanished. The future has not yet arrived. Neither has gone anywhere. They are all here, all at once, the way every frame of a film exists simultaneously on the reel even though the projector reveals them one at a time. This is the doctrine that philosophers call eternalism, and it is as strange to common sense as the rotation of the earth beneath our feet. Yet it follows directly from the relativity of simultaneity, which demonstrates that observers moving at different velocities disagree about which events are happening now, not because their clocks are wrong, but because there is no universal present moment to be right or wrong about. If two observers cannot agree on what constitutes the present, then the present cannot be the sole repository of reality. Some slice of space-time that one observer calls past, another calls present, and another calls future, and if all of them are describing the same universe, then past, present, and future must all be equally real features of it. The block contains them all. But then what are we to make of our experience? For we do not experience time as a static dimension. We feel it moving, flowing, carrying us forward like a current, each moment pressing against our backs, while the next opens before us. This sensation is so vivid, so insistent, so fundamental to the texture of consciousness, that to call it an illusion seems almost an act of violence against our own nature. And yet the brain is, among other things, an organ of narrative, a machine for stringing isolated moments into coherent stories, for stitching still photographs into the appearance of motion. It receives discrete snapshots of sensory data, none of which contains any trace of before or after in itself, and from these it weaves the seamless, flowing experience we call time. The smoothness of that experience is a construction, not a discovery. The brain does not perceive time's passage. It creates it, the way a storyteller creates continuity from a chain of events that are, in themselves, discontinuous. Some thinkers, confronting this, have argued that consciousness itself is what gives time its flow, that without a mind to observe the block, nothing in it would ever happen. Others maintain that the flow is a genuine feature of reality, and that the block universe, for all its mathematical elegance, leaves out something essential about what it feels like to be inside time. But if eternalism is correct, then every argument about the flow of time is an argument about the architecture of the mind, not the structure of the cosmos. The future is not approaching. The past is not receding. We are simply moving through a frozen landscape, and the motion we feel is our own. If time does not flow, if the river is still and only we move through it, then something else must give direction to our passage. Something must explain why we remember the past and not the future, why eggs break and do not unbreak, why the universe seems to run in one direction only. That something leads us, as it led Arthur Eddington a century ago, to a deceptively simple concept, and to the most inexorable law nature has ever revealed. Arthur Eddington was a man who understood stars, their interiors, their furnaces, the way they convert mass into the light that reaches us across parsecs of darkness. He led the expedition that confirmed Einstein's prediction that gravity bends starlight, and he was the first to describe the thermonuclear processes that make the sun shine. But in 1927, standing before an audience in Edinburgh, Eddington turned his attention to something at once more familiar and more elusive than any star. He called it the arrow of time. What Eddington observed was simply this, that there is a profound asymmetry in nature, a one-way quality woven into the very fabric of events. We never mistake a film running forward for the same film run in reverse. A teacup falls from a table and shatters into 100 fragments. It does not reassemble itself and leap back onto the table. Smoke billows from a chimney and disperses into the sky. It never gathers itself from the wind and descends, reconstituted, into the fireplace. A human being is born small and helpless, grows strong, and then grows frail. No one has ever observed the reverse. These are not coincidences. They are not local peculiarities. They are, Eddington said, all manifestations of a single law, the second law of thermodynamics, and that law is what gives time its direction. The second law is, in a quiet way, the most melancholy of all the laws of physics. It states that disorder, what physicists call entropy, always increases. A neat room left to itself grows cluttered. A hot cup of coffee on the counter cools to the temperature of the surrounding air. A mountain erodes into a plain. A living organism, exquisitely ordered in every cell, slowly loses its organization and dies. In each case, the universe moves from a state of improbable arrangement to a state of probable chaos, from structure to formlessness, from low entropy to high. Entropy is the measure of that disorder, and its steady, irreversible increase is what we experience as the passage of time. The arrow flies in the direction of increasing entropy. Consider a deck of 52 cards arranged in perfect sequence, ace through king, each suit in order. The arrangement is exceedingly improbable. There is only one such ordering among some 10 to the 67th power possible permutations. Shuffle the deck once, and the order is likely diminished. Shuffle it 1,000 times, and it becomes, with near certainty, a random jumble. The universe works the same way. Every collision of atoms, every chemical reaction, every photon absorbed and re-emitted, every heartbeat, and every supernova increases the total entropy of the cosmos. The arrow of time is not, then, a fundamental property of time itself, but a statistical consequence, the overwhelming mathematical probability that things will become more disordered. Time flows forward because the universe is falling, slowly and inexorably, from a state of astonishing order toward a state of maximum chaos. But where did that initial order come from? Why was the universe ever arranged at all? That question, which we will return to, points backward, toward the beginning of everything, toward a moment of such low entropy that 14 billion years of increasing disorder have still not exhausted it. For now, consider the end. If entropy always increases, it must someday reach a maximum. The stars will exhaust their fuel and gutter out. The galaxies will dim. Even the black holes, those patient consumers of light and matter, will evaporate by Hawking radiation until the last one winks out of existence. Every particle, every quantum of energy will be spread so uniformly across the inconceivable vastness of space that no temperature difference, no energy gradient, no usable information will remain. The universe will arrive at thermal equilibrium, a state of perfect, featureless sameness, sometimes called heat death. In that final stillness, nothing will happen because nothing can happen. There will be no stars to burn, no organisms to live and die, no teacups to shatter or hearts to break. And yet, and this is the strange and unsettling part, time itself may not end there. The arrow of time is not the same thing as time. The arrow is a direction, a bias, a tendency, imprinted on events by the fact that entropy is changing. But when entropy reaches its maximum and can increase no further, the arrow simply ceases to point. The dimension of time, the coordinate that Einstein wove into the fabric of space-time, may persist, as empty and as meaningless as a compass needle at the magnetic pole. Time without an arrow, time without change, time without witness. If time can exist without direction, if it is merely a coordinate and not a current, then perhaps the arrow is not as absolute as it appears. Perhaps, under conditions of extraordinary violence or extraordinary geometry, it could be bent or looped or made to point the other way. The equations of physics, at least, do not forbid it. The equations of general relativity are, in a certain sense, democratic. They describe how matter and energy curve the fabric of space-time, and how that curvature, in turn, guides the motion of matter and energy. When Einstein published them in 1915, he could not have suspected all the strange creatures that would crawl out of those equations. Creatures he would spend the later years of his life trying to push back in. Among them were solutions that permit closed time-like curves, paths through space-time that loop back upon themselves, returning a traveler to the very moment from which they departed. Kurt Gödel, the mathematician whose incompleteness theorems had already shaken the foundations of logic itself, found one such solution in 1949. Gödel's universe is not our universe. It rotates, slowly, majestically, like some immense carousel, every galaxy sweeping around a central axis. In such a cosmos, the rotation drags space-time itself into a spiral, and a sufficiently determined traveler, moving at ordinary speeds for a sufficiently long time, could circle the universe and arrive home before they left. Einstein was disturbed. The possibility that his own theory might permit travel into the past struck him as something close to a logical scandal. But Gödel's rotating universe was only the first of several such pathways. Black holes, those gravitational abysses from which not even light can escape, contain, in the mathematics, inner horizons where the equations seem to permit passage from one region of space-time to another, or from one time to another. And there are wormholes, tunnels connecting distant points in space and time, shortcuts through the fabric of the cosmos, the way a fold in a sheet of paper can bring two far-separated points into sudden, startling adjacency. Some of these solutions involve enormous rotating masses, others require negative curvature or singularities that spin. All of them demand conditions so extreme that they exist, if they exist at all, only in the most violent corners of the cosmos, in the cores of galaxies, in the collisions of neutron stars, in the first searing instant of the Big Bang itself. The question is whether the mathematics describes anything real, or merely exercises itself. And here the barriers rise, formidable, perhaps insurmountable. To hold a wormhole open, to prevent its throat from collapsing the instant it forms, requires something that has never been observed and may not exist at all. Exotic matter possessing negative energy density. Without such a substance propping the tunnel apart, it pinches shut faster than light could traverse it. The traveler would be crushed before arriving anywhere, let alone before. Can the past be visited without being altered? Can it be altered without being destroyed? Is history a river that can be stepped into twice, or a crystal, fixed and immutable? The equations do not say. They are, in their austere way, indifferent to our discomfort. And then there are the paradoxes. If you could travel into the past and prevent your grandfather from meeting your grandmother, if you could engineer your own non-existence, then you would never have been born to travel into the past in the first place. The chain of causality snaps. Effect precedes its cause, which precedes its effect, in an infinite regress that the human mind finds acutely distressing, though the laws of physics merely shrug. They do not distinguish between future and past. They never have. But there are workarounds, theoretical gambits that preserve the coherence of a universe permitting backward travel. One invokes parallel universes. Each journey into the past spawns a new branch of reality, and the traveler who alters history does so in a different timeline, leaving their own origin story intact. Another, proposed by the Russian physicist Igor Novikov, suggests that the universe is self-correcting, that any action taken by a time traveler must already have been part of history, because what happened already included the travelers going back. The gun jams, the letter is lost, the knife misses. The universe arranges itself to prevent contradiction, not by prohibition, but by the quiet tyranny of logical consistency. These are not idle amusements. They are serious proposals, debated in the pages of serious journals, examined in the only laboratory where such things can be tested, the computer. Simulations of space-time under extreme conditions, rotating singularities, colliding black holes, quantum fluctuations in the fabric of the early universe, may one day reveal whether these pathways to the past are genuine features of nature or mirages cast by an overambitious mathematics. For now, they remain open, neither confirmed nor foreclosed, a door that the laws of physics neither clearly lock nor clearly open. And yet, even if the past is forever beyond our reach, even if no pathway through the cosmos can carry us backward, a stranger question remains, whether the forward motion we feel, the steady, irreversible rush of moment into moment, is itself what it seems. For that question, we must look not to the stars, but to a photographer, a galloping horse, and a row of cameras lined up along a track in California. In the 1870s, along a sunlit racetrack in Sacramento, California, an English-born photographer named Eadweard Muybridge arranged a row of cameras at careful intervals and aimed them all at a galloping horse. The question that had driven him to this arrangement was, in its way, a humble one, the kind of thing a child might ask and a scientist might spend years pursuing. When a horse runs, does it ever lift all four hooves from the ground at once, or does one foot always remain in contact with the earth? The human eye could not settle the matter. The horse moved too fast, the moment of full suspension too brief, and the brain, that magnificent but limited instrument, could not freeze the instant long enough to examine it. So Muybridge built a machine to do what the eye could not. He stretched wires across the track, connected each to a camera shutter, and let the horse's own body trip the mechanism as it passed. The horse, in effect, photographed itself. What the cameras captured was a revelation. There, on glass plates coated with chemicals, was the animal in mid-stride, with all four legs gathered beneath its body, hanging in the air for a fragment of a second that no unaided human eye had ever witnessed. The debate was settled, but the photographs held a deeper discovery, one that Muybridge may not have anticipated, and that reaches far beyond the biomechanics of a horse's gait. Each individual image was perfectly still. Each frame was a frozen moment, complete and self-contained, containing no motion whatsoever. A horse with its forelegs extended, a horse with its hooves tucked, a horse suspended in the void between footfalls. In none of these photographs does anything move. In none of them does time flow. And yet, when we arrange them in sequence, when the eye passes from one plate to the next, the horse runs, the gallop returns, the motion lives. This is chronophotography, the dissection of movement into its constituent stillnesses, and it carries within it a disquieting suggestion, one that extends from a California racetrack to the foundations of reality itself. For what Muybridge accomplished with his row of cameras is precisely what the brain accomplishes in every waking moment of our lives. The eye does not perceive motion. It receives a sequence of still images, frozen snapshots of the world, each one a complete picture of a single instant. And the brain, that tireless interpreter, that restless fabricator of continuity, stitches them together into the smooth and unbroken flow we call experience. The passage of time, that relentless river we feel carrying us forward from moment to moment, may be no more real than the gallop of Muybridge's horse. Consider what happens when you sit in a darkened theater and watch a film. 24 frames pass before your eyes each second, each one a static image, each one utterly without motion. The projector illuminates a single frame, then darkness falls, then the next frame appears, then darkness again. Between the frames there is nothing, no horse, no movement, no time. And yet you see a woman walking through a doorway, a door swinging open, a train arriving at the station. The motion is not in the frames. It is in the comparison between them. It is constructed by the mind from the difference between one stillness and the next. This is not merely the mechanism of cinema. If the block universe is correct, it is the architecture of perception itself. Each moment of our lives may exist as a complete, frozen state, a frame in the cosmic sequence, containing everything that is at that instant, no more and no less. The past moments are not destroyed when we leave them. The future moments are not created when we arrive. They all exist, each one as still and complete as a glass plate in Muybridge's camera, each one an eternal now, embedded in the four-dimensional fabric of space-time. What we call the passage of time is the movement of our consciousness through these frames, comparing one to another, inferring change, manufacturing the illusion of flow from the accumulated differences between static, timeless states. The horse never moved. The motion was in us. But if the flow of time is an interpretation rather than a fundamental property of the universe, if what we feel as the river of moments is something the mind constructs from stillness, then we are compelled to ask a question that reaches back before photography, before cinema, before any instrument that could slice a second into pieces. We must ask what kind of thing time actually is, and whether the stage on which it seems to unfold, space itself, is as fixed and absolute as we have always believed, or whether it, too, dissolves when we look closely enough. Isaac Newton, a man who could calculate the trajectory of a cannonball, but could not navigate the simple corridors of human affection, conceived of space as a vast and invisible architecture, a container existing in its own right, independent of whatever it might hold. For Newton, space was the theater itself, constructed before any actor had been hired, before any script had been written, and it would remain standing, empty and patient, long after the last player had departed the stage. It was absolute. It was rigid. It was uncreated and eternal. And time, its inseparable companion, was the same, a universal clock, ticking at one identical rate everywhere, for everyone, beneath the surface of all phenomena, untouched by the events it measured. In this vision, the universe possessed a single, authoritative now that extended itself across the whole of the cosmos, like a crest of light moving across dark water, and every event, no matter how distant, could be assigned its precise and objective coordinate upon the great fixed grid. Against this vision stood Gottfried Wilhelm Leibniz, mathematician, diplomat, courtier, philosopher, a mind so fertile that he seems to have been attempting to populate the intellectual landscape the way a river in flood populates its delta. Leibniz regarded Newton's absolute space as not merely unsupported, but incoherent. How, he demanded, could one distinguish a universe in which every particle had been shifted 3 feet to the left from the original configuration? If space were a thing in itself, a substance with its own independent existence, then God would have had no sufficient reason to place the stars here rather than there. And God, in Leibniz's theology, always acts with sufficient reason, never capriciously, never without purpose. Space, he concluded, is nothing apart from the relations between bodies. It is the grammar of matter, not its container, the geometry of coexistence, not a box in which matter has been placed. Remove every particle, every field, every trembling grain of existence, and you have not merely emptied a room, you have abolished the very concepts of here and there, of near and far. Time, likewise, was no river flowing beneath the bridges of events, but simply the order of succession. This preceded that, and that is all that time can be said to mean. The debate consumed the years 1715 and 1716 in a famous exchange of letters between Leibniz and Samuel Clarke, Newton's friend, ally, and philosophical proxy. Some arguments turned on theology and the nature of God's choices, others on the observable mechanics of motion and the meaning of acceleration. Newton's absolute space had the undeniable virtue of being useful. His equations described the arc of a thrown stone and the stately procession of the planets with breathtaking accuracy, and they seemed to require a fixed and motionless background against which acceleration could be measured and understood. Leibniz's relational space had the different virtue of being logical. It violated no principle of reason, it postulated no mysterious, undetectable substance, and it demanded no explanation for why the Creator had chosen one orientation of the cosmos over another, because no such choice had ever been made. But who was right? Could space exist in a universe utterly emptied of matter, a theater without actors, a stage without players, a cathedral without congregation? Or would the stage itself dissolve the instant the last object vanished, the way silence ceases to be a thing at all when there is no ear to distinguish it from sound? Newton's equations conquered the solar system. They guided men in their imagination to the moons of Jupiter and the rings of Saturn. They predicted the return of comets and the timing of eclipses with a precision that seemed to ratify everything Newton had believed about the arena in which these events transpired. And so, for more than 2 centuries, his absolute space and absolute time stood unchallenged, not because anyone had ever proved them real, but because they worked so beautifully, so seamlessly, that no one needed to ask what they were. The question of what space and time actually are, as opposed to how they behave, was quietly set aside, the way a civilization sets aside any question it finds too vast or too uncomfortable, trusting that future generations will either answer it or forget it was ever asked. It would take a long time and a revolution that no one in the court of George I could have foreseen, to reveal that neither Newton nor Leibniz had been entirely right, that space is neither a rigid container nor a mere network of distances, but something far stranger, a thing that bends, that curves, that warps in the presence of matter, and carries the planets in its folds. But before that revolution, before the patent clerk and the beam of light, there remains a quieter question, one that Leibniz glimpsed at the edge of his argument, and that neither he nor Newton could answer. If space is nothing without the matter that defines it, and if time is nothing without the events that succeed one another within it, then what becomes of both when the universe runs down, when the last stars gutter out, when the last atoms drift apart, when there are no more events to order and no more matter to measure the distance between? Does the stage survive the departure of every actor, or does it too go dark? Picture then that far future when the last acts have all been played and the stagehands have gone home. The galaxies, those great spiral cities of 100 billion suns apiece, have receded beyond one another's horizons, carried apart by the relentless expansion of space, until each sits alone in a darkness it can no longer share. The stars have long since exhausted their nuclear fuel. Some collapsed to dense cinders that glowed faintly and faded. Some shed their outer atmospheres in concentric shells of gas that expanded and thinned and vanished into the void. Some simply guttered out, like candles at the end of a very long dinner. The universe has spent its thermodynamic inheritance. Every temperature gradient has been smoothed, every pocket of order dissolved into the uniform, featureless bath of maximum entropy. This is the heat death, not an explosion, not a conflagration, but a quiet cooling, a settling, the cosmos exhaling its last breath and finding nothing left to inhale. And in this gathering twilight, if twilight is even the word, for there is no dawn that follows it, consider the star whale, the last conscious being to swim the spaces between the dying galaxies. It has drifted for billions of years, sustaining itself on the faint residual warmth of the last white dwarfs, navigating by the gravitational whispers of black holes that themselves will evaporate, given enough patience, into a thin gruel of radiation. The star whale remembers. It remembers the age of galaxies, when light flooded the void and stars were born in fiery nurseries. It remembers, perhaps, the age of minds, when matter opened its eyes and wondered at the cosmos that had made it, and now it remembers alone, the last flicker of awareness in a universe grown cold. The question is not merely when the star whale dies, but what dies with it. For if time is, as Leibniz glimpsed at the edge of his argument, nothing more than the ordering of events, if it is the succession of moments, the before and after of things that happen, then a universe without events, without change, without a single observer to mark the passage from one instant to the next, may be a universe in which time has lost not merely its meaning, but its existence. Some thinkers have argued that time requires consciousness the way a falling tree requires a listener to make a sound, that without a mind to distinguish now from then, to hold a memory and anticipate a future, the very category of the temporal dissolves into nothing. Others have countered that time is woven into the fabric of reality itself, independent of any observer, that the universe kept its clocks long before the first eye opened and will keep them long after the last one closes. But this counter-argument falters in the deep future, where there are no clocks, no radioactive decay with a meaningful rate, no orbiting bodies, no entropy left to increase. What is a clock in a universe at thermal equilibrium? What is change in a cosmos where everything that will ever happen already has? The star whale, drifting through the last darkness, is the universe's final experiment in temporality. Its neurons fire, or whatever passes for neurons, whatever ancient biochemistry or exotic quantum process sustains its thought, and each firing is an event, a before and an after, a tiny island of time in an ever-widening atemporal sea. As long as it thinks, there is sequence. As long as it remembers, there is a past. As long as it dreads its own ending, however dimly, there is a future. The star whale carries time the way a deep-sea creature carries its own light, a small, warm thing in an immensity of cold. But the star whale, too, must die. Its energy is finite. The white dwarfs cool, the black holes evaporate. And when the last thought fades, when the last electrical impulse crosses the last synapse of the last mind in the cosmos, what remains? Not darkness, for darkness is something, a condition that presupposes an observer to name it. Not silence, for silence is the absence of sound, and absence requires a category to be absent from. Not even nothing, for nothing is a concept, and concepts require minds to hold them. There is only, what? The equations of physics, written in no hand, inscribed on no page, continuing to describe a universe that no longer describes itself to anyone. The metric tensor of general relativity still, in principle, assigns coordinates to spacetime. The wave function of quantum mechanics still, in principle, evolves. But evolves toward what? Measured by whom? Against what standard of before and after? Perhaps time, stripped of consciousness, stripped of change, stripped of entropy's slow climb, does not vanish so much as become irrelevant. A dimension without direction, a stage without actors, and without audience, and, if Leibniz was right, without even the scaffolding of space to hold it up. Perhaps it reverts to what it may always have been beneath our urgent, beating experience of it, a coordinate, static and indifferent, one number among four in the address of every event that ever was. Or perhaps, and here the question folds back upon itself like a serpent swallowing its tail, the star whale was never the thing that gave time its teeth. Perhaps consciousness was never the engine of temporal flow, but only its most vivid witness. Perhaps what drives the arrow of time forward, what makes the past fixed and the future open, what gives the universe its irreducible sense of direction, is something more fundamental than any mind, something buried in the information that the cosmos carries forward, and with every passing moment loses. In the middle of the 19th century, a Scottish physicist named James Clerk Maxwell, the same Maxwell whose equations would one day reveal light as an electromagnetic wave and bind electricity to magnetism in a single mathematical embrace, imagined a very small creature. It is not a demon in any theological sense, Maxwell assured his readers, but merely a being with faculties so acute that it can track the trajectory of every individual molecule in a vessel of gas. This demon stands guard at a tiny frictionless door between two chambers, both filled with gas at the same temperature. As molecules approach from either side, the demon opens and closes the door with perfect discrimination, allowing only the swift, energetic molecules to pass into one chamber, and only the slow, sluggish ones into the other. Gradually, inexorably, one chamber grows hot and the other cold. Heat has flowed from cold to hot. The entropy of the system has decreased. The second law of thermodynamics, that most implacable of physical statutes, the one that forbids the unmixing of coffee and cream, the unscrambling of an egg, the reassembly of a shattered teacup, appears to have been subverted by a vigilant doorman no larger than a molecule. For nearly a century, Maxwell's demon tormented physicists. It seemed to expose a crack in the foundations of thermodynamics, a loophole through which the arrow of time might be coaxed into running backward. If entropy could be made to decrease by an intelligence sufficiently clever and patient, then perhaps the forward march of disorder was not, after all, the deep structural law it appeared to be. Perhaps it was merely a consequence of our own laziness, our failure to sort things with sufficient care. Some physicists proposed that the demon's act of measurement itself must generate heat. Others argued that the mechanical operation of the door would inevitably dissipate energy. But each proposed resolution crumbled under closer scrutiny. No matter how carefully you accounted for the energy costs, you could always imagine a more efficient demon, a more frictionless door, a more cleverly designed apparatus that would seem to cheat the second law and reverse the arrow. The answer, when it finally came, arrived not from thermodynamics, but from a field that did not exist in Maxwell's time, the theory of information. In 1961, a physicist at IBM named Rolf Landauer demonstrated that computation itself is not free, or rather, that one specific kind of computation is not. You can copy information, you can move it from one place to another, you can read it and process it, all without any fundamental thermodynamic cost. But you cannot erase it. The act of erasure, the destruction of one bit of information, the resetting of a memory cell to a blank state, must, with mathematical inevitability, dissipate a minimum quantity of energy into the environment as heat. This is the Landauer limit, a quantity so infinitesimal that it is negligible in any ordinary engineering context, yet so fundamental that it is woven into the deepest fabric of physical reality. And here is where Maxwell's demon meets its reckoning. For the demon to sort molecules, it must first measure their velocities and then record those measurements in some form of memory, and that memory is finite. It must eventually be cleared to make room for new observations. Each time the demon erases a bit of stored information, it pays Landauer's price. The entropy generated by that erasure always exceeds, by a precise and calculable margin, the entropy the demon saved by sorting. The second law holds: The demon cannot win. The arrow of time does not reverse. What Landauer revealed was something far deeper than a clever resolution to a Victorian thought experiment. He showed that information is not an abstraction hovering above the physical world like a ghost above a graveyard. It is physical. Every bit of information is bound to a particular arrangement of matter and energy, and every irreversible destruction of information, every act of forgetting, generates entropy and pushes the universe one step further along its one-way road. The arrow of time, then, is not merely the increase of disorder. It is the steady, irreversible erasure of the universe's own memory, the loss, moment by moment, of the detailed record of where every molecule has been, what every photon has struck, which particular history produced this exact configuration of the world. The cosmos remembers less today than it did yesterday, and tomorrow it will remember less still. Forgetting, it turns out, is not something that merely happens to the universe. Forgetting is what the universe does. And yet this profound linking of information to entropy, this marriage of thermodynamics to computation, was itself only a beginning, a clue that the nature of time might be inseparable from something even stranger lurking beneath the classical world, something that would emerge when a quiet young physicist in Bristol wrote down an equation that married quantum mechanics to relativity and opened a door into a reality far stranger than Maxwell or Landauer could have imagined. The quiet young physicist was Paul Adrien Maurice Dirac, the son of a Swiss émigré schoolmaster in Bristol, a man so famously taciturn that his colleagues at Cambridge joked that an hour's conversation with him yielded a single spoken word, and that word was usually yes. But what Dirac lacked in loquacity he more than compensated for in mathematical audacity. In 1928, at the age of 26, he set himself what appeared to be a modest technical problem: to write down an equation describing the electron that would be consistent with Einstein's special theory of relativity. The existing quantum mechanics of Schrödinger and Heisenberg described the atomic world with astonishing accuracy, but it had been built for a universe of slow velocities and gentle energies, and Dirac, with the instinct of a composer who can hear a single false note amid an entire orchestra, found this neglect of relativity intolerable. What he produced was an equation of breathtaking economy, a handful of symbols arranged on a single line, and it accomplished far more than he had intended. The Dirac equation not only described the electron with relativistic precision, it demanded, with an almost prophetic certainty, the existence of an antiparticle, a mirror image electron bearing a positive charge, a creature that no one had observed and that many believed nature would have no reason to produce. When Carl Anderson detected the positron in cosmic ray tracks 4 years later, in 1932, the discovery was not really a surprise. It was a confirmation that the universe had been keeping a secret the mathematics had already whispered. But the true legacy of Dirac's equation was not the positron alone. It was the slow, dawning realization, gathering force through the 1930s and 1940s in the work of Feynman, Schwinger, Tomonaga, and others, that the marriage of quantum mechanics with special relativity demanded an entirely new conception of what reality is. Out of Dirac's insight was born quantum field theory, a framework in which particles are not tiny billiard balls rattling through a void, but rather localized excitations, ripples and vibrations in invisible fields that permeate the whole of existence. The electron is a wave in the electron field. The photon is a tremor in the electromagnetic field. Every quark, every neutrino, every fleeting muon is a momentary crest in an ocean of possibility extending to the farthest reaches of space, and these fields are never still. Even in the emptiest vacuum, even in the void between galaxies where matter has not been seen for 100 million light-years, there is a seething ferment, a quantum restlessness in which pairs of virtual particles flicker into existence and annihilate one another in intervals so brief that they borrow energy from nothing and return it before the universe can notice the debt. This was a triumph without parallel in the history of physics. Quantum field theory has survived every experimental test ever devised for it, predicting the magnetic moment of the electron to 10 decimal places, a precision equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. It is the most rigorously verified theoretical framework human beings have ever constructed, and yet it carries within it a wound that has refused to heal for nearly a century. For Dirac's equation, and all of quantum field theory that descended from it, was built upon the flat spacetime of Einstein's special relativity, a stage rigid, uniform, and unyielding, a geometry of straight lines. General relativity, Einstein's later and greater achievement, had revealed that space-time is not flat at all. It curves, it warps and bends in the presence of mass and energy, and it is this very curvature that we experience as gravity. Near a black hole, space-time folds in upon itself like a fabric crushed in a fist. Near the Big Bang, in that first inconceivable instant of cosmic birth, all of space and all of time are compressed into a region so small and so violent that the very notion of a smooth background dissolves. And here lies the impasse. Quantum field theory requires a fixed stage, a pre-existing space-time upon which the quantum fields perform their ceaseless dance. General relativity insists that the stage is itself a dancer, shaped and reshaped by everything that moves upon it. To describe the earliest moments of the universe, or the singularity at the heart of a black hole, or the fundamental nature of time itself, we need a single theory that is simultaneously quantum and gravitational, a theory in which space-time is not the backdrop, but part of the performance, in which geometry itself dissolves into the same probabilistic foam that governs particles. Despite decades of extraordinary effort, despite string theory and loop quantum gravity, and a dozen other approaches, each promising and each incomplete, no one has succeeded in writing down this theory. The two pillars of modern physics, each unassailable in its own domain, remain stubbornly, maddeningly incompatible. What this means for the nature of time is profound and unsettling. In general relativity, time is a dimension woven into the fabric of space-time, a coordinate that bends and stretches with gravity. In quantum field theory, time is an external parameter, a clock ticking outside the system, a silent metronome to which the fields keep their rhythm. These two conceptions cannot both be fundamental. Somewhere beneath them, in a theory we do not yet possess, time may reveal itself to be something stranger than either picture suggests. Not a dimension, not a parameter, but an emergent property, an illusion arising from the quantum entanglement of countless degrees of freedom, a ghost conjured by the structure of reality itself. And if time is not fundamental, if it can be stretched, compressed, perhaps even circumvented, then the question is not whether we can travel through it, but whether we are already traveling through it in ways we have only just begun to measure. We need not look to the remote extrapolations of theoretical physics to find time travelers. They have lived among us. One of them is a Russian cosmonaut named Sergei Krikalev, who spent 803 days in orbit, hurtling around the Earth at 28,000 kilometers per hour. For every second that elapsed for him, very slightly more than a second elapsed for those of us rooted to the surface below. When he returned, the cumulative difference amounted to roughly 1/50th of a second. He had, in the most literal and measurable sense, traveled into the future. The leap was infinitesimal, a fraction of a heartbeat, a gap no human being could ever perceive, but it was not zero, and it was not theoretical. It was recorded by atomic clocks, verified by instruments, and entered into the bureaucratic ledgers of space agencies that have no poetry whatsoever in them. What Krikalev accomplished by living, the Large Hadron Collider accomplishes by violence. Deep beneath the fields of the Swiss-French border, in a ring 27 kilometers in circumference, protons are accelerated to 99.999991% of the speed of light. At such velocities, the rules of ordinary experience collapse. The protons that streak through that underground cathedral experience time so dilated that a single second in their frame stretches, for an outside observer, across proportions that baffle every intuition nature has given us. A particle born to live for a mere fraction of a microsecond that should decay almost the instant of its creation persists, from our perspective, long enough to leave its tracks in detectors, to be measured, catalogued, named. It is, in effect, a visitor from a slower clock, dragged into our present and made to linger far beyond its appointed hour. This is not trickery. This is not metaphor. It is the direct and unavoidable consequence of a discovery made by a patent clerk in Bern in 1905, that the speed of light is the same for all observers, no matter how they move, and that if light's speed is fixed and absolute, then something else must yield. What yields is time. The faster you move through space, the slower you move through time. The two are not independent currencies, but a single account, and you cannot spend freely in one without withdrawing from the other. This is the bargain that reality strikes with every moving thing, from the snail crossing a garden wall to the photon crossing a galaxy, and no entity in the universe is exempt. Some objects move so slowly that their passage through time is nearly maximal. They age as swiftly as anything in the cosmos can age. Others, like Krikalev in his orbit, like the protons in their ring, like the muons that rain down from cosmic ray collisions in the upper atmosphere and should by all rights decay long before reaching the ground, move so fast that they borrow from time and pay in distance. The muons should not reach sea level. Their lifetimes are too brief, their decay too certain. But they do reach sea level, because at their velocities, time itself slows to a crawl, and what should be a death measured in microseconds becomes a marathon of endurance. We see them, we catch them in instruments. They are time travelers, and they have been arriving on this planet since before there was a planet to arrive on. And yet, for all its experimental certainty, for all the precision with which we have measured and confirmed and reconfirmed it, time dilation carries within it a disquiet that the equations themselves do nothing to resolve. If moving faster means aging slower, If a traveler could approach the speed of light and return to find that centuries had passed for the world he left behind, while only years had touched him, then time is not the universal, impartial river we once believed it to be. It is personal. It is local. It belongs to each observer, each clock, each frame of reference, and no two of them need agree on what is past, what is present, what is yet to come. But if time is so deeply relative, so thoroughly a matter of one's vantage point, then what, exactly, are the equations of physics actually describing? A coordinate, perhaps. A label, certainly, but a flow, a passage, something that moves? The more precisely we measure time, the more it seems to elude definition, and the stranger it becomes that we have built the entire architecture of cause and consequence upon something whose fundamental nature we cannot quite say what it is. Einstein dismantled the edifice of absolute time with the patience of a man who understood that the universe does not consult our preferences. Before him, Newton had conceived of time as flowing equably without relation to anything external, a river moving at one uniform rate through all the cosmos, the same for every observer, in every corner of space, unaffected by anything so trivial as motion or mass. It was a comforting vision. It was also wrong. Einstein showed that time bends, stretches, and compresses, that a clock on a speeding train ticks differently from one standing on the platform, that time itself warps in the gravitational embrace of a star. Two observers, moving relative to each other, will disagree not only about when something happens, but even about whether two events are simultaneous. The cosmic river, it turned out, was not one river at all, but many, branching, merging, flowing at different speeds, depending on where you stood and how fast you were moving. But here is the deeper strangeness, the one that haunts the foundations of physics. When Einstein's revolution settled, and the equations of relativity were written in their final, spare elegance, time had not merely been relativized, it had been, in a sense, frozen. In the mathematics of physics, time appears as a coordinate, a label no different in kind from the three coordinates of space. The equations do not describe a flowing, they describe a geometry. In the four-dimensional space-time of relativity, a particle's entire history, its past, present, and future, is laid out as a single curve, a world line threading through the block of space-time like a filament through glass. The equations tell you where the line goes. They do not tell you that anything is moving along it. This is not a limitation of the mathematics. It is, rather, a feature of them. The fundamental laws of physics, from Newton's mechanics to Maxwell's electromagnetism to the equations of general relativity themselves, are, almost without exception, time-symmetric. They work equally well forward and backward. Run the film of a planetary orbit in reverse, and the math raises no objection. A planet spiraling inward toward its sun and a planet spiraling outward away from it are both, as far as the equations are concerned, perfectly legitimate solutions. The laws do not know which way is future and which way is past. They contain no arrow, no current, no privileged instant called now, that sweeps forward and transforms future into past. In the equations, there is no becoming. There is only being, a frozen architecture of events, each one as real as any other, none of them happening in the way we experience happening. This is deeply peculiar. We feel time. We feel it the way we feel gravity or heat, as an immediate, irresistible fact of existence. The past is gone, the future is not yet, and the present is the razor's edge on which we balance, always falling forward. Our memories point one way, our intentions the other. Every thought, every heartbeat, every word spoken or left unspoken is carried onward on a current that we cannot pause or reverse. And yet none of this, none of it, appears in the fundamental equations. The physics knows nothing of flow. It knows only coordinates, relations, the elegant geometry of a four-dimensional block in which everything simply is. Some physicists have taken this to mean that the flow of time is an illusion, a trick of consciousness, a byproduct of how brains like ours process information, stitching together a sequence of static moments and calling the stitching a river. Others insist that the equations must be incomplete, that there is some deeper principle, not yet discovered, that will restore to time the flowing character our experience demands. But no such principle has been found, and so we are left in a strange position. The most successful physical theory ever devised describes a universe in which time does not flow, while every cell of our bodies, every fiber of our experience, insists that it does. Perhaps the resolution lies not in the equations themselves, but in something they do not yet contain, something about the early universe, about how it began, about why it started in such a peculiar and improbable state. For if time has no arrow in the fundamental laws, there is one place where an arrow unmistakably appears, in the slow, irreversible march of disorder, the relentless increase of entropy that turns hot coffee cold and topples empires and ages every living thing. The equations may be blind to the direction of time, but entropy is not. If entropy always increases, as the second law insists, then the further we look into the past, the lower it must have been. Follow the trail backward, through the slow cooling of the Earth, through the condensation of the first galaxies, through the opaque fireball of the early cosmos, and you arrive, inexorably, at a moment of extraordinary order. 14 billion years ago, the entire observable universe was compressed into a state of unimaginably low entropy, a hot, dense, almost perfectly smooth plasma in which every particle, every quantum of light, every fluctuation of the underlying fields was distributed with a precision that borders on the inconceivable. This is what physicists call the past hypothesis, the simple but sweeping assumption that the universe began in a condition of extraordinarily low entropy, and that everything that has happened since, every galaxy assembled and every star ignited, every ocean condensed and every organism evolved, has been a consequence of the cosmos climbing, by fitful and incremental and sometimes catastrophic stages, toward the maximum disorder that awaits it at the end. Consider what this means. Atomic theory tells us that matter is composed of particles, and that these particles can be arranged in vastly more disordered configurations than ordered ones. That for every orderly arrangement, there are trillions upon trillions of chaotic ones. The definition of entropy tells us that any system will tend, overwhelmingly and without exception, toward those more probable, more disordered states. Not because of any mechanical compulsion, not because of any force pushing it there, but simply because there are so many more ways to be disordered than to be ordered. And the past hypothesis tells us that, for reasons we do not yet understand and may never fully comprehend, the universe began in one of those staggeringly improbable ordered states. Combine these three ideas, the atomic nature of matter, the statistical meaning of entropy, and the low entropy origin of everything, and you have, remarkably, a complete explanation for all that has ever occurred. Every river that has carved a canyon from naked rock, every snowflake that has crystallized from moisture in a winter sky, every civilization that has risen in ambition and fallen into dust, none of these are violations of the second law. They are expressions of it. They are local eddies of order spinning within a universal current of disorder, made possible only because the universe began so far from equilibrium that there was low entropy energy to spend, structure to build, complexity to generate. The Earth does not defy thermodynamics by producing life. It merely borrows concentrated energy from the sun and radiates degraded heat into the void, and the difference pays for every leaf that unfurls, every heart that beats, every thought that has ever flickered into existence in a brain somewhere beneath the stars. Some have called the past hypothesis the greatest unexplained assumption in all of physics. Others have argued that it is not an assumption at all, but a clue, a window into the physics of the Big Bang itself, into whatever came before, into whatever process or principle selected a universe of such exquisite initial order from the incomprehensible space of possible universes that might have been. But whether it is assumption or clue, its explanatory power is without rival. With nothing more than atoms, entropy, and a low entropy beginning, we can account for the arrow of time, for the growth of structure across billions of years, for the possibility of life and the certainty of its eventual extinction. The universe, in this telling, is a clock that was wound up 14 billion years ago and has been unwinding ever since. We are creatures of the unwinding. Our memories, our histories, our deep intuitive sense that the past is fixed and the future is open, all of them ride the same thermodynamic gradient, the same slow cascade from order toward disorder. And yet, if time's arrow is fundamentally thermodynamic, if the flow we feel so vividly is nothing more than entropy increasing in our brains and in the world around us, then how much of what we experience as time is really out there in the fabric of the cosmos, and how much is in here, assembled by the mind from one fleeting moment to the next? The question is not merely philosophical. It can be approached experimentally, in the laboratory of the human brain, where a neuroscientist named David Eagleman devised an experiment so simple and so unsettling that it calls into question the very sequence of cause and effect on which we build our lives. A subject sits before a screen. She is asked to press a button. The button press triggers a flash of light, but with a deliberate delay, a fraction of a second too small for the conscious mind to register as a gap. The subject is then asked a straightforward question: which came first, your press of the button or the flash? The answer should be obvious. The subject pressed the button. The button caused the flash. The cause must precede the effect. This is not merely logic. It is the architecture of reality itself. And yet, when the delay falls within a certain window, somewhere in the range of a few tens of milliseconds, the subject reports that the flash appeared before she pressed the button. The effect has preceded its cause. The brain, confronted with two events so nearly simultaneous that it cannot reliably place them in sequence, does something extraordinary. It rewrites the order. It deposits the flash in the past, ahead of the action that produced it, as though time had briefly reversed itself in the private theater of a single mind. This is not a failure of attention or a trick of memory. It is something far more fundamental. The brain, it appears, does not experience the present moment as it unfolds. It collects sensory data over a brief integration window, a tenth of a second perhaps, during which the raw fragments of experience are held in a kind of suspension, unjudged and unordered, and only after that window closes does it render its verdict on what happened and in what sequence. The vivid, irresistible, now that we feel ourselves inhabiting, that razor edge between past and future, is not a knife-thin instant through which we slide. It is a retroactive construction assembled from fragments that have already arrived, already been processed, already been stitched together in the brain's slow and deliberate editing room. By the time we become conscious of the present, it is already past. Some moments stretch luxuriously, others compress to almost nothing. A frightening event, a car skidding on black ice, a fall from a great height, the suspended instant before an impact, seems to unfold in slow motion, as though time itself has obligingly dilated to accommodate the urgency of survival. Eagleman tested this too. He asked subjects to perform a task while falling through the air in a controlled descent, and afterward, he asked them to estimate how long the fall had lasted. He compared their estimates to the measured duration. The subjects consistently reported that the fall had lasted longer than it truly had, sometimes significantly longer. But here is the strangest and most revealing part. Their perception of time during the fall had not actually slowed. What had increased was the density of memory. Fear had sharpened attention, and sharpened attention had recorded the experience in far greater detail than ordinary experience receives. The brain, reading back this unusually rich record, inferred that a longer interval must have elapsed to contain it all. Time had not stretched. Memory had thickened. The slow motion present was an illusion constructed after the fact, from the weight of what had been remembered. If the sequencing of moments is a construction, and the perceived duration of those moments is also a construction, then what remains of time that is not in some sense a construction of the mind? The question takes on a clinical urgency when we consider those for whom the construction falters. In schizophrenia, the mind's capacity to organize experience into coherent temporal order begins to disintegrate. Thoughts arrive without discernible antecedents. Causes and effects become hopelessly entangled. The voice that speaks within the mind is mistaken for a voice from outside it, because the brain can no longer reliably place its own inner productions in the correct temporal sequence, cannot say, with confidence, "This thought is mine, and it came from there." What if schizophrenia is not, at its deepest root, a disorder of thought at all, but a disorder of time, a condition in which the delicate machinery that sequences our moments falters and stutters? What if the hallucinated voice is not a foreign intrusion, but a misordered production, the mind's own speech arriving out of sequence, stripped of its temporal signature? What if the terror of the illness is, at bottom, the terror of a mind that can no longer trust the order of its own moments? The implications radiate outward, from the clinic to the cosmos. If the arrow of time, that forward march we feel so powerfully in our bones, depends at least in part on the brain's capacity to integrate and order sensory data, then time as we experience it is not a feature of the universe, delivered to us whole and unambiguous. It is a filter. It is the specific manner in which a conscious organism, built from carbon and water and the faint electrical whispers of neurons, processes the raw, unordered information streaming in from a cosmos that may not, in itself, possess anything resembling a flowing present. The universe may not have a now. We may have the now. And if the now is something we generate rather than something we receive, then the next question becomes inescapable. If time is personal, assembled differently in every brain, shaped by velocity and gravity and the strange architecture of perception itself, then whose time is the true one, and does the cosmos, in its infancy, before there were minds to assemble it, experience time at all? There is a civilization, perhaps not unlike our own, that has lived long enough to witness the dimming. They have watched the galaxies drift apart, the stars exhaust their nuclear fuel, the cosmic background radiation cool toward absolute zero. They have migrated from world to world, harvested the dying embers of black holes, prolonged their existence by every ingenuity their science could devise. But the darkness is patient. It does not negotiate. And in the end, when the last usable gradient of heat has been spent, and the last thought has been thought, their world lines, those wavering threads that once traced through space-time like rivers through a continent, come to rest. What then is time? If no consciousness remains to distinguish one moment from the next, if no clock ticks and no memory forms, does the universe still possess a past and a future? Or has time always been something more modest than we imagined? Not a river flowing from event to event, not a stage upon which the cosmos performs, but simply a label, a coordinate, a way of telling one configuration of matter from another. We say the word 1,000 times a day, and rarely pause to wonder what we mean by it. We measure it with atoms and pendulums, feel it in our bones, mourn its passage, race against it. But perhaps it was never flowing at all. Perhaps it was only ever our way of making sense of a universe in which everything happens, all at once, forever. Some have argued that time without consciousness is nothing, that it requires an observer, a mind to sequence the frames, to compare one state with another, and call the difference duration. Others have insisted that time is woven into the fabric of reality itself, independent of any witness, enduring whether or not anyone remains to mark its passage. But if the block universe holds, if past, present, and future are all equally real, frozen in the geometry of space-time, then perhaps the question is backward. Time does not need us. It does not need the stars. It does not need the dying civilization or the last photon drifting through the void. It is simply there, as a coordinate is there, as a dimension is there, complete and changeless, holding every moment that ever was or will be in the same eternal architecture. The civilization is gone now. Their cities, their histories, their love and terror and longing, all preserved, if anything is preserved, in the indestructible record of space-time. The universe settles into equilibrium. No gradient remains. No arrow points anywhere. And yet, if the past endures as surely as the present once did, then nothing is truly lost. Every life, every world, every flicker of awareness that ever rose up against the darkness, all of it still exists, somewhere in the block, untouched by entropy, unreachable but unerasable. We began by asking what time is. Perhaps the honest answer is that we do not know, that we have never fully known, but we have learned this much, that we are the universe's way of knowing itself, briefly, in the narrow window between one darkness and the next. And if our moment is short, if our world lines are no more than brief sparks traced through the cold geometry of space-time, then they are sparks nonetheless, and the light they cast, however faint, is cast forever.